Hello everyone, it's Professor Sabatini here at Passaic County Community College, and today we're going to be doing Experiment 3 for Chem 111, which is the spectrophotometric analysis of food dye solutions. So what we're going to use today is an instrument called the spectrophotometer. A spectrophotometer is an instrument that has a light source, and you can filter that light source to shoot light, to beam light of a single wavelength through a sample. And then the spectrophotometer will measure the percent transmittance of light through that sample, so how much light actually gets through the sample. Depending on the color of your sample, we are measuring food dye. I'm using blue today. Depending on the color, different colors absorb different wavelengths of light. And in the first part of this experiment, we are going to find what is called the analytical wavelength for your particular sample. The analytical wavelength is the wavelength of light that your sample absorbs the most. This is important because when we use this wavelength for the rest of the experiment, and we will be finding a calibration curve where you will be measuring the absorbances of different samples that you will make that you know the concentration of. So you can plot the concentration of your sample versus the absorbance and get a calibration curve. And then using this calibration curve, you can determine the concentration of a sample that you don't know the concentration of by measuring its absorbance. And that's really the whole point of spectrophotometry in this aspect, is to measure the concentration of samples based on their absorbances. Okay? So the first thing we need to do is make a determine the analytical wavelength. So we're going to make an absorbance spectrum. So we're going to use the spectrophotometer, change the wavelength of light that is going through there, and measure the absorbance of your sample at different wavelengths so that we can find the wavelength that absorbs the best. Spectrophotometer here is a relatively simple machine on the outside. This is a little bit old school, but it works. We have here a knob to change the wavelength, so there is actually an analog dial here. I don't know if too many of you have seen analog in a while, but that's how we change the wavelength. And then also we have here, this is the sample holder. So that's where we will put our sample, and that's where the light will be going through. And the percent transmittance measured. All right. Also over here we have, this is called the zero absorbance 100% T button. So another thing we need to tell the spectrophotometer is what to blanket and give it, tell it what a sample that absorbs no light. For that, we're going to use distilled water. Right? Distilled water is clear, so it's not going to absorb any of these wavelengths of light. So we set the machine to 0 on that, and then we measure the absorbances of our sample. So the first things we're going to need are cuvettes. So these look like test tubes, but they're a little fancier than that because then they don't absorb any light. In one of these cuvettes, I'm going to put distilled water, and I'm going to fill that about 3/4 of the way. You don't want to fill it to the top, you don't need to. And in the other one, I'm going to put the food dye solution. All right. Now, when you're preparing your cuvettes, there's a few things that you want to remember before you run your sample. So first off, you need to clean this cuvette. Fingerprints absorb light, dirt, dust, whatever, absorb light, so you want to make sure they're nice and clean. And once you do that, if you handle it from the top, that would be beneficial because then you're not making it dirty and you don't have to clean it every time. So now that I clean these up, you also want to make sure there's no bubbles in there. Bubbles do not absorb light, and that will affect your readings and your accuracy. Okay, so now I'm going to run the analytical wavelength for this I'm going to find the analytical wavelength from a range of wavelengths from 360 to 700. Okay, so the procedure here is a bit tedious, but we'll get through it. All right, so I have my machine set at 360. I already turned this on and warmed it up. You want to warm up for about 15 minutes the lamp so that it is ready to go. And then here is the reading right here, and that's going to tell me the absorbance of the sample. So first, at 360 nanometers, I'm going to take this distilled water and I'm going to put it in the sample, close it up, and I'm going to push the 0 button because I'm going to tell it, well, this water is clear, it doesn't absorb any of this wavelength of light. Then when the machine tells me, it says that it's blanking the machine, which means I'm setting it to 0. It says 0, 0, 0. I realize that's kind of hard to see, but take my word for it. Then I take this out, and I put my sample in. And now I read the absorbance, and here it says 0.053. Now, the fun part, I get to repeat this process every 10 nanometers until I get to, say, 700 nanometers. So that's going to take a little while. But here we go. I take this back out, I put the water back in, change the wavelength to 370, 0. I wait for it to say 0. Takes a little while. And there we go. And then I put the sample back in, and I read the absorbance. Now it went up to 0.091. So I record that, and I keep repeating this, all right? Change the wavelength, water, 0. For the absorbance, 0.272. So we can see it's going up. Notice I grab the cuvettes by the top. I don't have to worry about constantly cleaning them because I'm not getting them dirty. So eventually, once I get all these done, I'm going to have a data table that has all these different wavelengths on it and their absorbances, and then I'm going to use Excel to plot those. It should also be known that sometimes the wavelengths will go up and down a little bit. The sample might absorb light at different wavelengths, differently. So it could absorb a little bit, like it could have a little peak lower down on the lower level of the wavelengths, and then again at a bigger one. You just want the highest peak. You want to find the wavelength that gives you the highest absorbance. screen went blank there for a minute. All right, I think you can see where I'm going with this, so I will spare you the rest of this. I'm going to go up to 660 nanometers every 10 nanometers. This process gets a little redundant, so I don't think we need to follow my every move here. So you can join me back for step 2 when we're preparing solutions, and we're going to make the calibration curve. All right, guys, we're back. I'm not going to lie, you missed out on a lot of exciting cuvette transferring and absorbance measuring, but I completed the data for my analytical my absorbance spectrum to find my analytical wavelength. I'll go over the graphing of that in a different video, but right now we're going to move on to part 2 of this experiment, which is to make a calibration curve. Now, from my data, I found that the wavelength of light that gave me the highest absorbance for that blue dye was 630 nanometers. So that's what I'm going to set my machine to when we're ready. The first thing we have to do, though, is make our solutions of known concentration. So we've been supplied with blue food dye. We know the concentration of this food dye. The food dye has a concentration that we know. I'll go over that in the calculations, so I don't need to do that right now. But then, since we know the concentration of that, we can dilute this, and we will know the concentrations of our solutions, A through E here. Okay? To make the solutions, what we're actually going to do is called making a serial dilution. And no, I'm not talking about putting milk in your Captain Crunch. I'm talking about we're going to dilute our solutions by the same amount each time. We are going to dilute these by half each time. So here, for my first part, I'm going to take my stock food dye solution using a pipette filler. I'm going to add 10 milliliters of this stock solution to beaker A here. Okay, so I put this pipette into my pipette filler snugly. The pipette here is graduated, right? It has marks. It actually has 2 different ways of marking it. One of them with the big numbers is kind of upside down. 0's at the top, 9's at the bottom, but if you drain it all out, it's 10. It's going down there. All right, we're adding 10, so I'm going to fill it to 0 and drain it all the way down. If you want, you could use the little numbers here, which you may or may not be able to see. Those are going from 10 down. So if you fill it up to that number and drain it, that's how much we're putting in. Regardless, I'm using 10. So I take my pipette with my pipette filler, and there's a dial on the back here. I'm going to roll that dial, and that will suck the liquid up into the pipette. All right, you can go a little bit past where you want, and then roll your thumb back down a little bit and get that meniscus right on the 10 or the 0. And then I put it in my beaker, and I drain out the pipette. Okay. Then I'm going to take a different pipette and dilute this with 10 milliliters of distilled water. Then I'm going to mix it up, and this is called solution A. This is going to be my most concentrated solution, and it'll have a concentration of half of the original dye solution. Now, I'm going to take the pipette I used for my food dye, rinse it out, a little bit of water so that you don't want to contaminate your samples here. Alright. Now, I'm going to take 10 milliliters of solution A and put it into B, beaker B. then take 10 milliliters of distilled water. And add it to B. So you can see what I've done. I've taken the stock solution, 10 milliliters stock solution, 10 milliliters of water, so it'll have half the concentration of the initial stock solution. That's for A. For B now, it's going to have half the concentration of A, because I took 10 milliliters of A and mixed it with 10 milliliters of water again. And I'm going to keep repeating that process until I get down to solution E. So remember, rinse out the pipette, rinsing it into my waste beaker. So I take 10 of B, put that in beaker C, of water, that in beaker C, rinse my dye pipette, mix up C, so 10 of C goes into beaker D, 10 of the water, goes into beaker D, mix that up nice, and then finally I'll rinse my pipette again. I take 10 of solution D, put that in beaker E, and I take 10 of my distilled water. So now I have 5 solutions that I know the concentrations of. And when we're doing a calibration curve, we want to see exactly how the concentration and the absorbance are related. So now I mix up E, and there we go. You can see here my solutions should get lighter, right, because I'm diluting them. So you can possibly kind of see that. And A is the darkest, E is the lightest, it's the most dilute. All right, so now I'm going to go back and check these absorbances. So I'm going to set my machine to my analytical wavelength there, 630. I'm going to blank the machine. Now, the good news here is I only have to blank the machine once. You only have to blank the machine when you're changing the wavelength. Right? After this, I don't change the wavelength anymore. I leave it at 630 because that's where it has the highest absorbance, and that's where it's going to have the highest sensitivity to differences in concentration. So I can just leave it at that. So now that it's at 0, I take this, and I'm going to use the same cuvette. You want to use the same cuvette to keep your readings consistent. So I'm going to dump out my distilled water, and I'm going to start with the solution that has the lowest concentration. So I'm going to start with E. That way, it's hard to completely empty the cuvette. I'm going to show you what to do here, but you want to always start with the solution with the lowest concentration That way, if there's a little bit left over, accidentally, it doesn't affect your results as much as if the concentrated one was in there. So you can see there's still a little bit of water in here, right? I can't get all the water out, so I'm going to take a little bit of my solution and pour it in there and actually rinse out the cuvette with that. Just a little, and I'll do it 2 times. Alright, then I'm going to fill it with my solution. So this is E. And then I'll just clean it up again, make sure. Gotta be nice and shiny. Put that in the machine, and now I read the absorbance. It's 0.065 for E. Now all I have to do is read the rest of them. So I take E, dump it in my waste beaker, get as much out as you can. Then I'm taking solution D, a little bit, and I'm rinsing it with the solution I actually want. So whatever gets trapped in there should be my solution. Pour that in. Remember, no bubbles, no fingerprints. And now my concentration should go up. 0.146. Sometimes when you're pouring these, a little bit of liquid slips out, spills out, so you want to make sure that's not on there. .289, which is looking good. It's going up. And then we do B. The tissue I'm using to wipe this is actually called a Kim wipe. It's fancy tissue. It doesn't have any lint. Lint. If it left behind lint, that would absorb light. So these are very fancy lint-free tissues. B is 0.592, and then I get to A, which is almost my last one. Up nice. .208. Alright, so those are my 5 solutions that I know the concentration of. So now I can make a calibration curve from that, where I plot the concentration of these solutions on the x-axis and the absorbance on the y-axis. And then I would get the best fit line and get the equation of that line. But calculations and stuff will be a different video. This is just procedural stuff. All right. The one more thing, though, that we want to do is, and what the whole purpose is to find the concentration of a solution based on its absorbance. So here, I'm rinsing this out with distilled water right now just to get rid of the concentrated solution. I have a solution that I don't know the concentration of. It's mysterious. It came from my lab instructor, or myself, because I'm the lab instructor. All right? But it's an unknown solution. It's the same dye, but I don't know the concentration. All right? Its concentration should be within the calibration curve. That's how it works. So I'm going to take this unknown solution, rinse out my cuvette again, because that is how you do it. And then I'm going to just simply record the absorbance of this unknown. The absorbance is 0.389. Now, just looking at this, and I don't know the concentrations right now, we didn't go over that, but the absorbance of the unknown is in between the absorbance of beaker C and beaker B. So its concentration will be in between the concentration of C and the concentration of B. That's how this works. The absorbance and the concentration of these solutions are directly related. It's called Beer's law. All right. If one solution has twice the absorbance of another solution, that means it has twice the concentration. If it would have half the absorbance, it would have half the concentration. And that's it. That's lab number 3, spectroscopy of food dye. I hope you guys had a great time watching. As great time as watching as I had making it. And yeah, the calculations on that will be taken care of on another